Hi everyone, so welcome to lecture 10. This is part 1 and we are going to talk about discrete choice and binary classification. Okay? So this first part is about binary classification models, more specifically about probit and logit and maximum likelihood estimation and penalized likelihood estimation in high dimensions. Okay? The references is our Hasty, Tibshiran and Friedman book, chapters 4 and 9, and also there's an additional reference to the book by Wooldridge, Econometric Analysis of Cross-Section. So far we have considered regression problems, and now we are going to move into classification problems or choice problems. And our dependent variable, y, will be binary. It will take values either 0 or 1, and this kind of setup appears in several important situations. For example, if you want to know the occurrence of certain events, it is raining or not, asset returns are positive or not, a firm is bankrupted or not, a customer will default or not, or individual behavior like choice. Should I read a book or watch TV? Should I take a job A or job B? And classification. A given email is spam or not, an image is a cat or not, a given operation is fraudulent or not. Okay? So these are all situations where binary dependent variables are very important and is like the target variable to be explained. Okay? So there are many applications where target variables binary, like credit analysis, fraud detection, image recognition, and many more. Okay? Usually our interest will lie in the conditional probability. So what's the probability of y being equal to 1 given x, where x is a set of explanatory variables, right? So a joke here, but if you look at images, which images represent Marcelo? So you feed the model with all these images, and you have to decide which of these images represent Marcelo and which images do not represent Marcelo. So one important thing, we are going to make a change of notation, because as many of the problems involving binary dependent variables are on the cross-section and not time series, we will adopt the index I instead of t. So I will run from 1 to n, and is the sample size, okay? So far we have considered models of continuous variables y with continuous covariate. So we have a regression where y is x prime beta plus u, okay? And the question is, do you think this model is a good option when y take values on 0 and 1 when it's binary? And the answer is no, and why is no? Okay, because since y is a Bernoulli random variable, the model implies that the condition expectation of y on x is exactly the probability of y equal to 1 given x, that which is x beta if you have a linear model, okay? But since covariate x are continuous, potentially unbounded variables, okay, the range for x beta goes from minus infinity to infinity, okay? But the conditional probability should be restricted to the interval 0, 1. Okay, so, and then you have kind of a problem here, because your model will imply that y varies between minus infinity and infinity, but we know that y takes only two possible values, either 1 or 0. Okay, so basically, if you have your data, imagine that you have x, and then you have y's, and that's what a typical scatter plot of y and x you see. You see a bunch of zeros and a bunch of ones. And if you run a regression with this data, that's your fit. It would be a terrible fit because we are going to try to fit a line on this data, and it's clear from this picture that this is not a good fit. Okay? So how we are going to solve the problem? We have to redefine the dependent variable. Okay, so the linear model is clearly not a good fit for binary dependent variables. So we have to do something else. Okay, so in that example, the line goes below 0 and above 1. So you can tell that probabilities are outside the range between 0 and 1, which of course makes no sense. Okay, so how can we solve this problem? So let's focus attention on the conditional probability instead of y. Okay, and the idea is that we can use a function that we are going to call g from R that maps values on the reals to the interval, the closed interval 0, 1, to consistently map x beta into this conditional probability. Okay, the probability of y equal to 1 given x. So we are going basically to write that the probability of y being equal to 1 given x is this nonlinear function g of x beta. Okay? So choosing different g's will generate different models among them. Okay? So Probit and Logit are two of the most popular models. Okay, so let's look into the Probit. So the idea is to choose G as the Gaussian cumulative distribution function, the CDF. Okay, that we are going to call phi. So we say that the probability of y equals to 1 given x is phi of x beta. Okay, and the inverse probability, phi inverse, is x beta, and phi is displayed on your slides. Okay, so this model was proposed based on the use of a link function f that maps the probability into the real line. Okay, and the link function here, f, is just the inverse of the CDF, and this is called the Probit link. Okay, and the term was created by biologists in the 1930s and means like probability unit. Okay? And what's the Logit model? The Logit model, the choice for G is the logistic CDF instead of the Gaussian CDF. Okay? So why is the Logit model attractive? Originally, it was much easier to estimate and compute than the Probit because it does not involve that integral. Okay, it's much easier to generalize to multiple classes like multinomial models, as we are going to see during the second block. Okay, so the logistic CDF, you see, it's much simpler expression because it's a ratio of exponentials. Okay, so we can write the probability of y equals to 1 given x is the exponential of x beta divided by 1 plus the exponential of x beta. Okay? And that's the Gaussian CDF, and that's the logistic CDF. You see they're kind of pretty much similar. Okay? And why are CDF type transformations helpful? Okay? Look at our example where you have the scatter plot of the x's and y's, and these are the kind of the circles, the blue circles. So we have here like Logit fits with beta equal to 10, 20, and 50. Okay. In this case, because the pairs x and y are linearly separable into two classes within the X covariant space, okay, the CDF type function perfectly separates them. It perfectly fits the y's. Okay? So in this situation where the two classes, 0, 1, are linearly separable. Okay? So we can also look into the problem through the lens of what's so-called odds ratio. Okay? And we saw that the linear probability model, implied by the usual linear regression, generates an incompatibility, okay? Because between the probabilities and the range of the model. Okay? And we saw that by picking a CDF to work as this function g, we can map x beta into 0, 1 and solve the problem, okay? But there is an alternative way of making the conditional probability and x beta compatible, okay? Is to look at from another angle and finding a transformation that maps the probability, so maps the 0, 1 interval into the open interval between minus infinity and infinity, okay? And I'm just going to show the derivation of the logit model using this alternative. Okay? So let's look at the definition of an odds ratio. So an odds ratio is a statistic that quantifies the strength of the association between two events. So let's say that we have like two events, A and B. The odds ratio is the ratio of the odds of A in the presence of B and the odds of A in the absence of B, okay? And or equivalently, due to symmetry, the ratio of the odds of B in the presence of A and the odds of B in the absence of A, okay? So let's look at an example. If some event occurs with probability P, then the odds of it happening, that we're going to call OP, is P divided by 1 minus P. So it's the ratio of the probabilities of the two events, okay? So the probability of A divided by the probability of its complement, okay? So P equal to 0, OP is 0, P goes to 1/4, OP is 1/3, so odds are 1 to 3 against, P half, OP is 1, even odds, P 3/4, OP is 3, so odds are 3 to 1 in favor, P equals to 1, OP infinity. Okay, so this is kind of the basic definition. So takes the original variable, that's binary, 0, 1, okay? The probability function, let's call P, okay? And it's continuous between 0 and 1. Okay? So taking the odds of y occurring is P divided by 1 minus P. So we map the unit interval into the non-negative real line, 0, infinity. Okay? A final step, we take the log of the odds ratio, okay, which maps 0, infinity into minus infinity, infinity. Okay? So this is the logit function, is the log of the odds ratio. So it's the log of P divided by 1 minus P. Okay? So that's the plot of, for the logit function, the probability of success and the log odds ratio. Okay? So you see we map from 0 and 1 into minus infinity and infinity on the real line. Okay? So this is kind of a way like to motivate why is the logit. So you can just take a very simple approach that say, okay, we just need a CDF between 0 and 1 and that's it, and we pick the logit CDF, or we can pick the probit CDF, or we can even take any CDF, okay? So we pick these two for simplicity, okay? Or you can take a derivation of the logit in terms of the odd ratio and you arrive at the same conclusions, okay? And what I'm going to show you now is how like to give an interpretation of these models, which is very common in economics and might be useful in several applications in finance. Okay, what are these betas really representing? And this is why that's kind of the root of these choice methods. So we're going to look at latent variable models. Okay, so consider the following model, that we have an y star that's linearly related to x. Okay, it was like the usual regression. So y star is x prime beta plus u, but we do not observe y star. Y star is a latent variable. What we observe is y. Okay, and y is equal to 1 if y star is positive, and y equals to 0 if y star is equal to 0 or negative. Okay, so we only observe realizations of y and x. Y star we do not observe. So as I mentioned, y star is a latent variable. So therefore, y star will be larger than 0 if x beta plus u is larger than 0. So if u is larger than minus x beta. Okay? So consequently, the probability of y star larger than 0 given x is the probability of y equals to 1 given x, which is the probability of u larger than minus x beta, which is equal to the probability of u being less than x prime beta. Okay, so we need to make assumptions on the error term in order to compute the probability above. Okay, so what's the simplest error that we can imagine? Gaussian. Okay, so if we assume that u is a normal with zero mean and unit variance, okay, we have the probability of y star larger than 0 given x is the probability of y equal to 1 given x, which is the probability of u being less than x prime beta, but as u is a standard normal, that's just phi x beta, and then we derived the probit model. Okay, so that's another way of deriving the probit model, coming from a latent variable. So the logit you can derive from odds ratio. The probit we can define from latent variable models, and as we are going to see, the latent variable model is very interesting to interpret this kind of models as choice models. As we are going to see, this y star can be like differences into utilities concerning different choices. Okay, and an individual will choose A instead of B depending on the difference of utility functions. Okay. Oh, similarly, the probability of y equals to 0 is just y 1 minus phi of x beta. Okay. But how can we derive the logit from the same kind of using the same reasoning? So suppose that instead of assuming that u is normally distributed, we consider that u has a logistic distribution. In this case, we get the logit model. Okay? So we can also derive the logit model using this latent variable approach. So, what's the shape of a logistic distribution that we are talking here so much? So the probability density function of the logistic distribution is displayed on your slide, and for different values of the location parameter mu and the scale parameter sigma, you have different plots. Okay? So in some cases, like the one in purple or the blue, it looks very much like a normal random variable with like fatter tails. Okay? So these are examples of the logistic PDF. Okay? All right. So now how can we estimate these models? Okay, so far I'm not talking anything about like large dimensions or fancy machine learning methods. This is the kind of the very basics of binary choice models. And I decided to start with these because this is like having a lecture on simple linear regression, but these are kind of important because in order to have the building blocks to arrive at very complex machine learning methods for classification, we need to know what's the simplest approach that we can take, like to describe binary dependent variables. Okay, so let's say that we have a sample that X is low dimension. How can we estimate the model? So suppose that Yx is a sequence of independent and identically distributed random variables, okay? And suppose also that P is less than N is fixed. So yeah, we are in fact in the low dimension environment, okay? Note that the conditional on realizations of X, Y is a Bernoulli random variable with probability of success given by the probability of Y equals to 1 given X, that we are going to write for simplicity lowercase p x beta. Okay? So we can write the likelihood, the instantaneous likelihood of this Bernoulli random variable, which should be this function g to the power of y, 1 minus g to the power of 1 minus y. This is the instantaneous likelihood. And the likelihood function, because the data is IID, is just the product, okay, of these instantaneous likelihoods, this instantaneous probability, okay, with individual probability. So this is kind of very basic statistics. So this is the likelihood function for Bernoulli random variable, okay, where the probabilities, the probability of success is written in terms of a g function with argument that is x beta. So if we take logs, we have y log of g, 1 minus y log 1 minus g. If we take the sum of this thing, because the product becomes the sum, okay? And then we have this term here, okay? So this is the log likelihood of Bernoulli random variable, where the probabilities are given by, the probability of success is given by g of x beta. So how we are going to estimate the parameters? What are the unknown parameters? The beta is the vector of beta. So how we are going to do that? We are going to maximize this function. Okay? So you see now that it's pretty different from what we have from linear regression, because in linear regression we were just minimizing the sum of the squared errors. Okay? Here we are maximizing the likelihood. Okay? The likelihood function, because we have a well-defined probability model where we have assumptions. We know what's the model, the probability model that describes the y's conditional on x, okay? And this expression has nothing to do with the g, the choice of g. Then now we have to make a choice and select a g function that so far we took like the simplest way, where g can be probit or logit. Okay. Of course, as we are going to see, this can be much more complicated, but so far that's what we have. Okay. So beta will be given by the estimate will be beta hat will be the argument that minimizes the negative of the log likelihood, because this is exactly the same as maximizing the log likelihood. So we are going to minimize this expression. Of course, there's no closed formula. Okay, so we have to run iterative optimization algorithms to solve this minimization program. Okay, and so we have to rely on numerical methods. Okay. So now I'm moving to a little bit more technical things, but I think it would be important for us to fully understand this model. Okay, so what we can expect about the estimates of the parameters. Okay? So basically, what we can say about the asymptotic distribution of the maximum likelihood estimators. Do they have the same properties of an OLS estimator in a linear regression? Okay, so the first thing we have to do is that we have to compute the derivative of the log likelihood function. So if we take the log likelihood and we are going to take the derivatives with respect to beta, that's what we find in the end of the day, where we define this lowercase g function is the derivative of the g function with respect to its argument. Okay, so it's defined here. Okay, so therefore we can compute also the second derivative. We take the derivative of the derivative, we take the expected value, we evaluate at beta equals to beta naught, which beta naught is like a true and true between double quotes, true parameter. Okay, we have this expression. Why we are doing that? Recall your probability, your basic statistics classes about maximum likelihood estimation and the properties of the maximum likelihood estimator. Like what's the variance of the maximum likelihood estimator? It depends on exactly on that quantity here, which is the Hessian. Okay, that's the expected value of the second derivative. Okay? So this depends on this nonlinear term here, and another term that resembles at what we have in linear models, that x prime. Okay? So we can show that the gradient will converge to a random Gaussian variable. Okay? And that's what's important here. Right? Square root n beta hat minus beta naught converging distribution to a normal random variable with zero mean, and that's the variance. Okay? So we can test hypotheses, we can conduct inference. Okay? And this closed formula easy to compute. So, but this is low dimension. Okay? And as you see here, his result holds for any g function which maps R into 0, 1. Okay? Continuous, no? Yes. Okay, because g must have like the first derivative. Okay? So it's a very general result that we can use. As we are going to see, of course, this does not hold in large dimensions. Okay? Unfortunately, it's much more complicated, the problem. Okay? Um, but how we should like give interpretation for the betas? Okay, so can we compute like partial effects? So let's recall what's the probability of y equal to 1 given x. So any cumulative distribution works. Two good choices, probe it and load it. Okay, so we have here. But now, differently from a linear model, the partial effects are not beta anymore. So if we take the derivative of p with respect to x, what we have is like lowercase g beta. So what's the partial effect? It's like what will happen to the probability if we make a change on the axis. So if x increased by 1%, how do we expect to happen? What's going to happen with the probability of y being equal to 1? So if the income of an individual is 1% higher, what's the probability of that individual defaulting on a loan? Okay, so you want to, if you want to you estimate a probit or a loaded model, you want to check if the betas are making sense. You want to, as I keep mentioning during this course, we don't want like to apply these models blindly. We want to understand what's going on. We want to give an interpretation. We want to explain why things are the way they are. So if we have a binary choice model, we have to like see what are those betas, what are they meaning for us. And one way to see that is to compute the partial effects. But the partial effects are not beta, the betas themselves. Now, differently from a linear model, we have this nonlinear function here. And in fact, the partial effect is not constant anymore. It depends on x. Okay? So we have more complication here. Okay? Okay? So the partial effect depends on x via lowercase g of x beta. Okay? And one thing is that if we look at ratios of the partial effects with respect to two variables, then of course this term here cancels, and we have just the ratio of the betas, but these are kind of more of limited importance. Okay? So relative effects do not depend on x, but absolute effects depend on x. Okay? So we should decide for which x we want to report the partial effect. Okay? So one thing is the partial effect at the average. Okay? So we evaluate the partial effects on the average x. So we are looking at departures from the average. Okay? So we can choose other points as well, like the median or any other quantile. Okay? Another possibility is to report the average partial effect. Okay? So we basically, we took the average of the g functions over all the observations, and we multiply by our estimate beta. Okay? So this is kind of two important things. So something for you to think and discuss. Which is better? Here or A? We can discuss more about that on Friday. So another important thing is that statistical significance of beta does not imply the statistical significance of the partial effects. Okay, so So from how can we show that? From basic statistics, let's assume that the statistics data is such that it converges to a normal. Okay. So we are going to use the delta method to get the asymptotic variance of the partial effect. So the square root and of a function of this statistic will be a Gaussian random variable with zero mean, and the variance given by this product of three terms here, where h is the gradient of the function. Okay. So when applied to our partial effects, what we can show, I'm going to skip like all these details, and let's move to the bigger picture. Is that the partial effect, okay, of the logit model, okay, is normal, but the covariance matrix is given by this expression here, okay, where this v hat is given by this expression, okay, and this thing here is the derivative of the function h with respect to beta. Okay? So it's also normal, but the variance is different. So a significant beta does not imply a significant partial effect, because the variances can be very different. Okay? All right. Okay. I hope everything is clear. So you don't have to really bother about the details of these computations. This all comes from a basic maximum likelihood theory. But it is that what you have to keep in mind is that, okay, with maximum likelihood, we can estimate in low dimensions. Okay, we have an asymptotic theory for the beta hat. This is like we have closed formula from that. Okay, but beta does not represent like partial effects. So we have to compute the solution is ape or PIA, like the average partial effects or partial effects on the average. Both these things are also normal with closed formula for the variance. So basically, inference is possible and easy to carry. Okay, so any package works of that. You can easily estimate this in Python, in R, and MATLAB, or you can implement from scratch. Okay, it's pretty easy, but so far low dimension. Okay, but once we have these probability models, how can we make decisions? Okay, because the probit or the logit, they will give us just the probability of y equals to 1 given a realization of x. Okay, so if you want to just make a decision, should I give a low one to an individual or not? Is the market going up or down tomorrow? We just have probability. How can we make decisions based on that probability? Okay, So suppose that y represents the dichotomic decision of giving or not giving credit to an individual I. As the output of the model is this continuous variable between 0 and 1, we must decide the cutoff value to make our decision. Okay? And suppose that we estimate this probability equals to 0.7. Should we give or not credit to this individual? Okay? So the choice of the cutoff point will depend on the application. So if the probability is above 0.6, give credit. If it's below, do not give. But you can be more strict. Only if the probability is 0.9. So you have to decide, and that's user defined. There's nothing that we can pick from. It's not something that the model will give us. Okay? All right. So the first part, the last part of this block one, we're going to look, okay, but how can we evaluate binary models, okay? The first way of evaluating if a binary model is like, if it has a good fit, because with regression we have R-squares, we have MSEs, we have a bunch of metrics that we can evaluate models. But how can we do that with binary models? So the first thing is the confusion matrix, where we have like the actual outcomes and the predicted values in a table. So it's a 2 by 2 table with 4 entries. And we have like the first one, the upper left part is that we're going to call it the true positive. The number of positive cases that are classified correctly as positive by the model. Note that here you need to make a cutoff to make your decisions, right? So this is depending on the cutoff that we discussed in the previous slide. FP is the false positive. The number of negative cases that are classified incorrectly as positive by the model. Then we have like true negative, number of negative cases that are classified correctly as negative, and false negative, number of positive cases that are classified incorrectly as negative. So we define the accuracy as the sum of the true positives and the true negatives divided by all the sum of all the entries. So a perfect model won't have any false positive and false negative. So we have like the true positive and true negative divided by true positive and true negatives, and the accuracy will be equal to 1. Okay? If it's a poor model that only makes mistakes, TP and TN will be equal to 0, so accuracy will be 0. So you have something between 0 and 1, okay? The closer is it to 1, the best is the model, okay? So that's called confusion matrix. The other way of looking at the methods, see if the model is good, is look at the Hawk curve, like the receiver operating characteristic curve. So it's the plot of the true positive rate, like the true positive divided by all the sum of the entries of the confusion matrix against the false positive rate. Okay, so if we have a straight line here, the model is worthless. So it's like just you're just like flipping a coin, okay, to decide if it's success or failure. Okay, if you have some kind of the purple line, it's a good model, but it will be an excellent model if it's very steep curve here. Okay, so you get like true positive rates and very low positive with respect to the false positive rate. Okay? So this is what the kind of model that one. The perfect model will have something like this, and this will be the perfect model. That basically you only have like true positives. Okay? Other ways to evaluate is like just look at the information criteria. minus 2 the log likelihood, plus 2p will be the AIC, minus 2 the log likelihood, and log np will be the BIC. One important thing, this is the for the Bernoulli random variables, right? Don't look at the likelihood of a linear regression where we assume Gaussianity. Okay. There's also the pseudo R squared, that's 1 minus the model likelihood or the null model likelihood, and the null model is just a model with a constant. You also can look at the deviance, that's just the minus 2 times the log likelihood. Okay, these are kind of other metrics that we can use to compare models. Okay. So finally, how can we estimate these models in high dimensions? It's pretty easy. Basically, we do penalized maximum likelihood. So we augment the log likelihood by the penalty, like the ridge, the lasso, the adaptive lasso, the elastic net. Simple as that. And all packages that estimate for a linear regression can do with binary models. Okay, logit. Usually logit, probit is not implemented in all of them. It's implemented in GLMNet in R, but it's not implemented in Python as far as I know. Okay, properties of these estimators much more complicated. Okay, doing inference much more complicated. Still kind of open problem of ongoing research. Okay, but we can estimate these models in large dimensions. Okay, so that's it for now, and I see you on block 2.